Have you ever watched a $2,500 car embarrass a $56,000 machine? Not because of fancy parts, not because of a turbocharged setup bolted on over a weekend, but because of something that most people in the modern automotive world have completely forgotten exists? What if I told you that right now, hidden in small garages across America, there are mechanics who possess knowledge so refined, so deeply understood, that they can extract performance from an engine that billion-dollar manufacturers with supercomputers and wind tunnels simply cannot replicate? And what if I told you that these mechanics, the ones who figured all of this out, learned their craft not in a technical school, not from a YouTube channel, but from fixing broken tractors in rural Mexico during harvest season when failure was not an option? This is legacy motoring, and I spend way too much time thinking about forgotten mechanical arts and the underground racing culture that kept them alive. If you're someone who loves the real story behind automotive performance, the stuff that never makes it into mainstream car magazines or factory press releases, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Because today we are going deep. We are talking about a period in American street racing history that fundamentally changed how serious builders think about engine performance. We are talking about immigrant mechanics from Mexico, Guatemala, Honduras, the Dominican Republic, and Puerto Rico who were, in the late 1990s and early 2000s, consistently and repeatedly beating factory-tuned cars worth 10 times more. And they were doing it not with expensive electronics, not with exotic materials, but with wrenches, timing lights, hand files, and decades of hands-on experience that the modern automotive industry had quietly decided was no longer necessary. Here's the thing. The automotive industry made a decision somewhere in the late 1980s and into the 1990s. It decided that computer management systems were the future, that mechanical precision would be handled by sensors and processors, and that the old ways of understanding an engine at a fundamental physical level were relic. Manufacturers started designing engines with tolerances that assumed electronic compensation. They built in inefficiencies that the ECU would paper over. They trained an entire generation of technicians to plug in diagnostic tools and follow fault codes rather than listen to the engine, smell the exhaust, or feel the vibration through their fingertip. But here is what most people do not realize. In countries where replacement parts were scarce, where the nearest dealer was 300 miles away, and where a broken tractor during harvest meant a family went hungry, mechanics never made that transition. They stayed rooted in fundamentals because they had no choice. And when those mechanics immigrated to the United States, they brought with them something that money genuinely cannot buy: a complete, intuitive, physics-based understanding of how an internal combustion engine actually worked. Picture this. It is 2001. An abandoned industrial road outside Los Angeles, somewhere in the maze of warehouses and freight yards east of downtown, where the streetlights are sparse and the only audience is other gearheads who drove out specifically to witness what happens when old school meets new school. On one side of the road sits a brand new BMW M3, the E46 generation, a car that at the time represented the absolute pinnacle of mainstream performance engineering. It cost $56,000 new. Its inline-six produced 333 horsepower using BMW's S54 engine, which at the time was considered one of the finest naturally aspirated production engines ever built. BMW's motorsport division had spent years developing it. Engineers with advanced degrees had optimized it using computational fluid dynamics software and precision machine tools that cost more than most houses. On the other side of that road sits a 1992 Honda Civic. It has 180,000 miles on the odometer. The paint has seen better days. The interior smells like someone's uncle's garage. The asking price on a good day may be $2,500. The engine, when you start it, sounds like a sewing machine with respiratory issues. The BMW driver revs his engine. It sounds like a symphony. He is smiling. He is not particularly worried. The flag drops. What happens next is the kind of thing that makes you question everything you thought you understood about performance. The Civic launches like it has been fired from a cannon. 2 car lengths before the BMW driver has even fully committed to the throttle. By the quarter-mile marker, the Honda is 3 car lengths ahead, having just run a 12.88-second pass. The BMW ran 13.4. In the world of drag racing, that gap is not close. That is a demolition. The BMW driver demands to see under the hood. What he finds does not compute. There is no aftermarket engine management system. No nitrous bottle. No external plumbing suggesting a hidden turbocharger. What he sees instead is an engine bay so immaculate it looks surgical. Every bolt is safety wired like an aircraft component. Every vacuum line has been replaced with silicone. The timing marks on the crank pulley are painted in what appears to be bright red nail polish. The ports on the intake manifold have been hand-smoothed to a finish that catches the light. The man responsible for this car is standing nearby. His name is Miguel Santos. He is 58 years old. He learned to work on engines in the 1960s, fixing agricultural equipment in rural Mexico. He has never used a computer diagnostic tool in his life. He has been a mechanic for over 40 years, and in that time, he has developed an understanding of internal combustion that most modern trained technicians will never come close to matching. And here is where it gets really interesting. This was not a fluke. This was not one lucky night. This was happening consistently, repeatedly, all over America. Immigrant mechanics were taking cars that dealerships had given up on, cars with odometers that had lapped twice, cars that polite society had written off as transportation appliances, and turning them into machines capable of running with and beating supercars. They were doing it using techniques that had been removed from automotive curriculums, techniques that modern technical schools did not bother teaching because the industry had decided that software had made them obsolete. They were the keepers of something the industry had abandoned, and they were proving, on real roads with real time slips, that their way was not just different. Sometimes it was better. To understand how this underground revolution happened, we need to go back to where these mechanics learned their craft, because the origin story is as important as the result. In rural Mexico in the 1960s and 1970s, a mechanic did not have the luxury of ordering a replacement part and waiting 3 days for it to arrive. A mechanic did not have a diagnostic computer that would tell him which sensor had failed. A mechanic had his hands, his ears, his nose, his eyes, and the accumulated knowledge passed down from whoever taught him. Miguel Santos learned from his father, who was the only mechanic in a farming community of 2,000 people. By age 12, Miguel could rebuild a carburetor blindfolded. Not because someone made him practice it until he could do it blind, but because he had done it so many times, in so many different conditions, with so many variations in wear and contamination and fuel quality, that his hands simply knew. By 16, he was porting cylinder heads with hand files. He did not call it porting. He called it smoothing. He knew that rough surfaces inside the intake passages created turbulence, and that turbulence disrupted the organized flow of air into the combustion chamber. He knew that a smoother port meant more air got where it needed to go. He knew this not from reading a textbook, but from building engines that made more power when he smoothed the ports and less power when he did not. That is a fundamentally different kind of knowledge than reading about it. That knowledge lives in the hands. When Miguel immigrated to Los Angeles in 1987, he found work at a small garage in East LA. The work was mostly straightforward repairs for other immigrants, people who could not afford dealership pricing and needed someone they trusted. But Miguel noticed something almost immediately. The modern fuel-injected cars that everyone was driving had been built with compromises. Manufacturers had grown comfortable letting computer systems compensate for mechanical inefficiencies. The engines were fine. They ran. They met emissions standards. They passed inspection. But they were not optimized. They were adequate, and there is a massive difference between adequate and optimized. By the late 1990s, the import tuner scene was exploding across Southern California. Teenagers and young adults were buying Honda Civics, Acura Integras, and Mitsubishi Eclipses and trying to make them fast. The mainstream approach was simple: bolt-on aftermarket parts, cold air intake, aftermarket headers, a larger exhaust, and then spend $1,000 on a programmable engine management system. Companies like AEM, HKS, and Apexi were printing money selling plug-and-play solutions that promised effortless horsepower gains. The formula was well established and widely understood. Buy parts, bolt them on, send it to the dyno, get a tune, repeat. Here is the thing though. While the bolt-on crowd was stacking parts onto fundamentally compromised foundations, mechanics like Miguel were asking a completely different question. Instead of asking what can I add, they were asking what is being lost and where. Because here is what most people do not realize. An engine is fundamentally an air pump. Its efficiency depends on how well it moves air from the atmosphere, through the intake system, into the combustion chamber, and back out through the exhaust. Every rough surface, every misalignment, every imbalance, every inefficiency in that process costs you power. And if you pile aftermarket parts onto a fundamentally inefficient foundation, you are making something that was imperfect faster at being imperfect. Let me walk you through what Miguel would actually do when a Honda B16A engine sat on his stand, because this is where the real education happens. The B16A is the 1.6-liter VTEC four-cylinder that powered the Civic C and the Del Sol VTEC, among others. Honda rated it at 160 horsepower from the factory, which was genuinely impressive for a 1.6-liter engine in the early 1990s. It had a sophisticated variable valve timing system and revved to 8,500 RPM. It was considered one of the better small displacement performance engines available in that price range. Miguel would start by completely disassembling it. Not just the head. Everything. Every single component would come out, get cleaned in solvent, measured, catalogued, and inspected. He would check the block deck height with a precision straight edge, because even a variation of 0.02 of an inch across the deck surface could affect compression ratios differently between cylinders, creating power imbalances that no tune could fully correct. He would measure bore diameter at multiple points and multiple depths in each cylinder, looking for taper and out-of-round conditions. He would measure every bearing journal, every rod, every piston. He was building a complete picture of the engine's actual condition rather than its theoretical specification. Then came the cylinder head, and this is where the 40 years of hand skill separated Miguel from every other builder in the region. Honda's factory casting process left the intake and exhaust ports with relatively rough surfaces. This was unavoidable at production scale. You cannot hand-finish every port on every engine coming off a manufacturing line. The roughness created turbulence, and turbulence is the enemy of volumetric efficiency. Miguel would spend 20 hours on a single cylinder head, reshaping each port with hand files and progressively finer sandpaper. He was not making them bigger. That is a critical point. Making a port larger reduces air velocity, and velocity is what you need to fill the combustion chamber efficiently. He was making them smoother and reshaping the curvature of the short side radius on the intake ports, maintaining velocity while eliminating the turbulent separation that cost power. Now you might be thinking, okay, modern shops have CNC porting machines that can do this in a fraction of the time. And that is true. But here is where Miguel's hand finishing had an actual technical advantage. Every port in a production casting is slightly different. The casting process introduces minor variations in wall thickness, in the exact shape of the port cross-section, in the position of casting seams. A CNC program cuts the same path on every port regardless of where each port actually starts. A human eye, trained over decades, can adapt to each port's unique characteristics and optimize accordingly. The machine is consistent. The craftsman is precise. The valve job received equal obsession. Factory valve seats were cut with 3 angles: 30 degrees, 45 degrees, and 60 degrees. Miguel cut 5 angles, sometimes 7. Each transition carefully calculated to smooth the airflow around the valve as it opened. He would narrow the valve seats from the factory specification of 60 thousandths of an inch down to 40 thousandths, which reduced the contact area between valve and seat, improved heat transfer out of the valve, and marginally improved flow at low lift. Then he would back-cut the valves themselves, removing material from the back face of each valve to reduce weight and improve the flow characteristics around the valve head. But the combustion chamber work was perhaps the most technically significant step. Factory production heads showed chamber volumes that varied by as much as 2 cubic centimeters between cylinders. 2 cc sounds insignificant until you realize that this means compression ratios are not equal across the engine. Different compression ratios mean different power outputs per cylinder, which means the engine is not running at its potential. Miguel would measure every combustion chamber with a graduated burette and a piece of plexiglass, filling each chamber with solvent to determine its exact volume. Then he would carefully remove material from the larger chambers until every single one measured exactly 42.5 cubic centimeters. He would then polish each chamber to a mirror finish, not for aesthetics, but because smooth surfaces eliminated hot spots that could cause pre-ignition and allowed him to run more ignition advance before detonation became a risk. The bottom end received the same treatment. Factory pistons had casting marks and surface irregularities that contributed to windage losses at high RPM. Miguel would smooth every piston surface. He would knife-edge the connecting rod beams, tapering them so they cut through the crankcase oil mist rather than slapping against it. He would balance the entire rotating assembly to within half a gram. At 8,000 RPM, the crankshaft completes 133 full rotations every second. Any imbalance at that speed creates harmonics that rob power and accelerate wear on every bearing surface in the engine. The intake manifold received port matching work, carefully aligning the manifold runners with the head ports so there was no step, no ledge, no disruption for the airflow to stumble over at the transition. Thermal barrier coatings were applied by hand to the piston crowns and combustion chamber surfaces, keeping heat energy in the combustion event rather than letting it soak into the metal. Exhaust ports received ceramic coating to maintain exhaust gas velocity by preventing heat loss through the port walls. Every single modification was grounded in physics, not in a parts catalog, not in a forum thread, in physics, and the results were measurable and consistent. A stock B16A made approximately 160 horsepower at the crank. A bolt-on modified B16A with intake, header, exhaust, and an ECU tune typically made around 175 horsepower. Miguel's engines, using those same bolt-on parts but with his foundational optimization work done first, consistently made 195 to 200 horsepower. That is a 15% advantage from optimization alone, before you add a single aftermarket component. The technical reason comes down to volumetric efficiency. A stock B16A achieved roughly 85% volumetric efficiency at peak torque, meaning the cylinders were only filling to 85% of their theoretical capacity. Miguel's work pushed this above 95%. At 8,000 RPM, that 10 percentage point improvement meant each cylinder was ingesting significantly more air per cycle. More air meant more fuel could be burned. More fuel burned meant more energy released. More energy meant more power at the crankshaft. The power delivery characteristic of Miguel's engines was something that impressed even people who were not focused on outright numbers. Modern tuned engines, especially in the bolt-on community, often had pronounced flat spots where power dropped off between the low and high cam profiles of Honda's VTEC system. The transition could be abrupt enough to unsettle the chassis under acceleration, particularly mid-corner. Miguel's engines had none of that. The power built progressively and linearly from idle to redline, which made them dramatically easier to drive at the limit and allowed drivers to extract more of the engine's potential more consistently. Part of that came from the balanced rotating assembly. When every piston and rod combination weighs exactly the same amount and the crankshaft is dynamically balanced, the engine does not fight itself as it revs. The tachometer needle sweeps smoothly rather than hunting and jumping. The chassis does not experience the pulsing vibration that comes from an unbalanced rotating assembly shaking itself against its mount. The driver receives cleaner feedback from the car because there is less mechanical noise obscuring the useful information. Look, the fuel system work that Miguel applied was another area where old-school methodology outperformed modern technology. The fashionable approach in the late 1990s was to install larger fuel injectors and an adjustable fuel pressure regulator, then try to tune around them with a programmable ECU. The problem with this approach is that larger injectors have shorter minimum pulse widths, which makes fine fuel control at idle and light cruise genuinely difficult. The ECU has to work harder to maintain an accurate mixture, and the results were often rough idle quality and increased fuel consumption outside of the power band. Miguel would instead flow test the stock injectors on a bench, measuring the actual fuel delivery of each one across a range of pulse widths and fuel pressures. Factory injectors typically varied from each other by 5 to 8% in actual flow rate. He would match them within 1%, sometimes less, sorting through sets of injectors from salvage yard engines until he had 4 that performed identically. He would then modify the fuel rail to eliminate pressure drop from one end to the other, ensuring that every injector saw identical fuel pressure regardless of which one was opening at any given moment. He would clock each injector, rotating it slightly within its O-ring seal until its spray pattern was optimally positioned within the port for that cylinder's specific airflow direction. The result was cylinder-to-cylinder fuel distribution that modern fuel-injected engines still struggle to match, even with sophisticated injection strategies and direct injection systems. When you have perfectly balanced injectors delivering exactly the right amount of fuel into perfectly matched ports, every cylinder makes the same power. The engine is not an average of its cylinders. It is the product of all of them working in harmony. Ignition timing optimization was where the contrast between Miguel's approach and the computer-tuned approach became most dramatic. Most tuners using programmable ECUs in that era would download a base map from an online forum, make some adjustments based on fuel type and compression ratio, and call the engine done after a couple of dyno pulls. The base maps were conservative because they had to work across a range of engines in different conditions, which meant they left power on the table. Miguel used a timing light and his ears, in the most literal sense. He would run the engine at a specific RPM and load condition, then advance the timing incrementally, 1 degree at a time, listening for the faint metallic knock that indicated detonation onset. He would back off 2 degrees from that point and record it. He would repeat this process across the entire operating range, building a timing curve from feel and auditory feedback rather than from sensors and software. He understood from experience that cylinder number 4, positioned farthest from the water pump in a transverse-mounted 4-cylinder, ran measurably hotter than cylinder number 1, and needed 2 degrees less advance to avoid detonation at the same conditions. He compensated for this intuitively because he had seen it hundreds of times. The transmission received attention that most builders completely overlooked. Synchronizer rings were polished and the clearances set precisely, which reduced the effort required to engage each gear and allowed faster shifts without grinding. Gear sets were rim polished on a buffing wheel to reduce friction between gear teeth during engagement. Shift forks were carefully weighed and lightened where material could be safely removed without compromising strength. The final result was a gearbox that shifted with less effort and less time between gears than any aftermarket short shifter kit could achieve, because the reduction in rotating inertia from all the lightning work allowed the engine and transmission to synchronize speeds faster during each shift. Suspension setup was another domain where Miguel's knowledge went far beyond the standard approach. The import tuner community in the late 1990s had largely adopted a formula: by a set of coilovers, lower the car as much as possible without the wheels rubbing, and declare it done. The assumption was that lower meant faster, and that aftermarket dampers were automatically better than stock ones. Miguel understood this was a cartoon version of suspension tuning. He would spend hours corner-weighting cars using 4 bathroom scales, one under each wheel, adjusting the spring perch heights in small increments until the cross-weight balance was perfect. Cross-weight, or the diagonal weight relationship between corners of the car, has a profound effect on how the car responds to throttle input at launch and how it transitions under braking. A car with improperly set cross-weight will pull to one side under hard acceleration, which on a dragstrip translates directly to lost time as the driver corrects rather than accelerating cleanly. He modified bump stops to precisely control the suspension travel at the limit of compression, preventing abrupt contact that would spike the wheel load and brake traction. He would clock the springs within the coilover bodies, rotating them so that the coil compression force aligned perfectly with the damper axis, preventing the binding that off-axis spring force creates in most coilover installations. He understood that a binding suspension does not respond to road irregularities properly, which on an imperfect road surface translates to inconsistent traction. Tire pressure optimization alone, according to Miguel, was worth half a second in a quarter-mile pass on a radial tire. He did not simply inflate to the specification on the sidewall. He understood the thermal behavior of the tire compound. At launch, a slightly lower pressure in the drive wheels increased the contact patch and improved grip off the line. As the tires heated through the run, the air inside expanded, raising the pressure naturally toward the optimal value for high-speed stability. He would start a drag pass at 28 psi in the rear tires, knowing that a proper burnout would bring them up to 32 psi by the time the car staged at the line. That was the number he wanted at launch, and the further pressure rise through the run was accounted for in his starting point. Word spread through the Latino community the way useful information always spreads in tight-knit communities, through direct experience and trusted recommendation. One person brought a car to Miguel, got results that seemed impossible, and told 3 people. Those 3 told 3 more. Within a couple of years, his garage had become a genuine pilgrimage site. People drove from other cities to have their engines built there. The waiting list for a complete engine build grew to months. But this was not just one man working in isolation. Miguel had apprentices, and those apprentices were learning in the same way he had learned. By watching, by doing, by feeling. Young mechanics would work in his shop for free in exchange for the education. They would watch him check valve guide clearance by feel, running a valve stem through the guide and detecting where through his fingertips that no measurement instrument was sensitive enough to reveal. They would watch him identify bearing damage by drawing his thumbnail across the bearing surface and feeling imperfections measured in millionths of an inch. And then they would do it themselves, with him correcting their technique until they developed the same sensitivity. This apprenticeship model created a network of specialized mechanics across Southern California, each with their own area of deepest expertise, but all sharing the same fundamental philosophy. Understand the physics, optimize everything, trust your senses. Roberto, working out of a garage in Pomona, became the region's acknowledged authority on forced induction. Not the kind of forced induction where you bolt a turbocharger kit onto a stock engine and hope it holds together, but the kind where you understand heat rejection, compressor maps, turbine housing sizing, and boost timing as a complete thermodynamic system. Roberto could pair turbocharger components from 2 completely different vehicles, understanding each component's individual characteristics well enough to predict how they would interact, and produce a setup that a kit manufacturer with millions in engineering budget could not match for response and efficiency. His approach to intercoolers was a perfect example of the old-school methodology applied to modern technology. While most builders simply chose the largest intercooler that would physically fit and connected it with the shortest pipe runs possible, Roberto mapped the thermal load of his engine across a full power run and designed the intercooler sizing to match that specific heat rejection requirement. An oversized intercooler was not better in his view, because it added volume to the system that increased turbo lag and slowed throttle response. The correct size was the one that handled the heat without being larger than necessary. Carlos, operating out of Long Beach, had developed an expertise in automatic transmission modification that made his setups shift faster and more reliably than dual-clutch transmissions in back-to-back testing. His secret was understanding that automatic transmission behavior is determined by hydraulic circuit timing, valve body calibration, and accumulator piston tuning, all of which could be adjusted with hand tools and a thorough understanding of fluid dynamics. He would rework the valve body on a 4-speed automatic until it shifted with a crispness that felt violent by production car standards, eliminating the soft, cushioned shifts that manufacturers built in to protect the drivetrain and improve perceived refinement at the expense of shift speed. Juan, based in Santa Ana, was the suspension specialist whose reputation extended into the professional racing community. Juan had figured out, through years of experimentation on the street and at track days, that spring rate alone meant almost nothing as a specification. What mattered was motion ratio, the relationship between suspension travel and spring compression at any given point in the suspension's range of motion. He had mapped the motion ratios of every common Honda and Nissan suspension configuration through careful measurement, and he used this data to select spring rates that produced the wheel rate he wanted rather than the spring rate that the parts catalog advertised. He understood damping ratios and how to evaluate whether a shock absorber was properly matched to a spring. He had developed a feel for damper behavior by bouncing corner after corner of different cars, learning what appropriate damping felt like through his hands and body rather than through electronic measurement. When a chassis tester with a computerized damper evaluation system was brought to a track day where Juan was working, its readings aligned within 5% of his manual assessments across 12 different damper setups. The engineers operating the machine were not particularly surprised. Juan was. The street racing scene that these mechanics fed became a proving ground for their techniques in the most direct possible way. Every weekend night, the industrial zones around Commerce, Vernon, and Irwindale became improvised quarter-mile strips where time slips were real and the results were unambiguous. There was no dyno number to argue about, no magazine test to dispute. You either ran the time or you did not. A properly prepared, naturally aspirated B16A Honda, built the way Miguel built them, was running mid-12-second quarter miles in 2001. To put that in historical context, a Ferrari 360 Medina ran 12.8 seconds in contemporary magazine testing. A Porsche 911 Turbo ran 12.5. These were vehicles costing between $150,000 and $200,000, and they were being matched by cars that had been bought for $2,000 and built in a small East LA garage using hand tools and knowledge that the automotive industry had classified as obsolete. The cost comparison was not lost on anyone paying attention. A complete programmable engine management system from a reputable manufacturer cost $1,500 to $2,000 at the time. Professional dyno tuning for that system added $500 to $1,000 more. Electronic boost controllers, wideband oxygen sensors, data logging equipment, and supporting hardware could push the total well past $5,000 just for the electronics alone. Miguel's complete engine optimization, including the machine work, the hand porting, the balancing, and the assembly, was priced at approximately $3,000. The results were better in power output and substantially better in reliability. Reliability was, in many ways, the most impressive proof of concept. The bolt-on community was accustomed to engine failures. A popular forum at the time had entire sections dedicated to what was euphemistically called the learning process of building a performance engine, which was understood to mean the first one probably would not survive. Budget turbocharged Hondas had a reputation for spectacular failures when tuning was slightly off or parts did not cooperate as expected. A blown engine in a $2,000 Civic was expensive in percentage terms. Miguel's naturally aspirated builds were different. His engines were not just fast in the short term, they were genuinely durable. The attention to balancing and clearancing eliminated the stress concentrations and harmonic vibrations that cause premature bearing failures. The careful thermal management, the coating work and heat shielding, prevented the localized overheating that cracks heads and warps valves. The precise fuel distribution ensured no cylinder ran lean under any condition. These engines ran hard and lasted. Drivers who had Miguel's work reported running 150,000 miles of hard use, including regular track days and drag events, without major failures. The engines were not babied. They were raced. They just did not break. Now you might be thinking, if this approach is so effective, why did not mainstream performance shops adopt it? Why did the industry not bring these techniques back into the fold? And the answer to that is partly economic and partly cultural. Hand-porting a cylinder head for 20 hours at a skilled mechanic's labor rate made the final cost of that service high enough that most customers would look at the price and choose a less labor-intensive alternative. In a market where a bolt-on intake costs $200 and claims 15 horsepower on a dyno, a service that required 20 hours of skilled labor to produce 15 additional horsepower on top of the bolt-on results was a genuinely difficult sell to anyone without a deep enough commitment to performance to do the arithmetic carefully. The cultural dimension was separate and worth understanding on its own terms. The import tuner scene of the late 1990s and early 2000s was driven largely by young enthusiasts who absorbed their values and techniques from magazines like Super Street and Sport Compact Car, from early internet forums, and from the film The Fast and the Furious, which was released in 2001 and promptly made everyone in the country aware that Honda Civics could be fast. That culture valued visible modification. It valued parts with brand names. It valued being able to point to specific components and explain what they did. A smoothly ported cylinder head that looks identical to a stock one from the outside offered nothing in that social currency. What Miguel's work produced was performance without a story that fit the existing narrative. When someone asked what he had done to the engine to make it so fast, the honest answer was 30 years of experience applied over several weeks of careful work. And that answer did not fit on a sticker. Here is what most people do not realize about the technical principles that made these builds so effective. None of them were secret. Every technique Miguel used was documented in engineering literature dating back to the 1950s and 1960s. Philip Smith's book on exhaust and intake system design, Colin Campbell's work on the sports car engine, and Ricardo's foundational research on combustion chamber geometry all describe these principles in precise technical detail. The knowledge had not been lost in the sense that it had been destroyed. It had been lost in the sense that the modern industry had decided it was no longer economically worthwhile to apply it, and training institutions had stopped teaching it. When Honda's engineering staff eventually became aware of what was happening in garages like Miguel's, their response was more thoughtful than dismissive. Some engineers initially insisted that their designs had been optimized on flow benches that cost more than most small businesses were worth, using software that ran fluid dynamic simulations at a level of detail that no human could replicate manually. And they were not wrong. The simulation capability of a major manufacturer in 2001 was genuinely impressive by any reasonable standard. But the issue was never that the manufacturers did not know how to optimize an engine. The issue was that mass production imposed constraints that hand builders did not face. A production engine had to function correctly on fuel ranging from 87 to 93 octane. It had to survive being operated by owners who never checked the oil, who idled for 20 minutes on cold mornings in Minnesota winters, and who ran the air conditioning at full power in Phoenix summers. It had to meet federal emissions standards throughout its production life. It had to be assembled on a line by workers of varying skill levels using tools calibrated to manufacturing tolerances rather than performance tolerances. And it had to cost a specific amount to produce to hit a price point that the market would accept. Miguel's engines faced none of those constraints. He was building for one customer, one use case, one performance target. He could use fuel with a known octane rating every time. He could assume the owner would maintain oil levels and coolant condition. He could tune for peak power without worrying about a catalyst that would wear out if exhaust temperatures ran too high. He was free to optimize in a way that mass production structurally prevents, and the results of that freedom were what showed up on the timeslip. Honda eventually sent a small group of engineers to spend time in several of the more accomplished independent performance shops in Southern California, including Miguel's operation. They came with clipboards and cameras and questions. What they observed gave them material that fed back into later production designs in subtle ways. The combustion chamber geometry of Honda's K-Series engines, which replaced the B-Series in 2001, showed evidence of exactly the kind of careful radius work that Miguel had been applying by hand to the earlier engines. The fuel rail design on the K20 eliminated the pressure drop issues that Miguel had been correcting manually on B-Series fuel rails for years. Whether these represented direct influence from what the engineers observed in the field or parallel development would be difficult to establish definitively. But the correlation was not lost on people who knew both stories. The data logging revolution that arrived for amateur builders around 2004 and 2005 provided something genuinely valuable: objective confirmation of what these mechanics knew subjectively. When affordable wide-band air-fuel ratio monitors and simple data loggers became accessible to the performance community, people could finally see in numbers what was happening inside their engines throughout a run rather than extrapolating from a dyno graph taken at steady state on a roller. And what the data showed validated the old-school approach in a way that no amount of argument had been able to accomplish. Engines tuned by the traditional mechanical methods showed air-fuel ratios that were consistent and stable throughout the RPM range and across all cylinders. Ignition timing curves, reconstructed from combustion pressure data, matched what professional tuners using far more sophisticated equipment would later define as minimum advance for best torque timing across the operating range. The empirical methods had produced results that the theoretical methods confirmed as correct. The experience had been right all along. The data just made it legible to a new generation that had learned to trust numbers more than craft. The technical innovations that these mechanics developed independently deserve recognition as genuine contributions to automotive engineering knowledge. Anti-reversion chambers in exhaust headers, small expansions immediately downstream of the exhaust port that reduce the pressure wave reflection that pushes exhaust gases back into the cylinder at certain RPM ranges, were being fabricated by hand by several of these mechanics before they appeared as a design feature in aftermarket header catalogs. The underlying principle was understood from experience, from observing that headers built with this feature ran more strongly across a broader RPM range, before the theoretical explanation became widely discussed. The discovery that dimpling intake port surfaces, in a pattern inspired by the dimples on a golf ball, reduced boundary layer separation in certain port geometries was another independently arrived at conclusion. Golf balls carry dimples because they reduce drag by promoting turbulent flow in the boundary layer immediately adjacent to the ball's surface, which delays the separation of that layer and reduces the large low-pressure wake that causes drag. The same principle, applied to intake ports where the airflow must navigate a curve, can prevent the separation of airflow from the port wall that would otherwise create a turbulent dead zone and reduce effective port area. Miguel had been doing this, calling it rough finishing in certain areas. 4 years before the fluid dynamics explanation became part of the performance community's vocabulary. The use of molybdenum disulfide as a coating on high-load contact surfaces like rocker arms and cam lobes represented another area where these mechanics had arrived at effective practice ahead of mainstream adoption. Moly, as it was commonly called, reduced friction between metal surfaces through a mechanism different from conventional oil lubrication, bonding to the metal surface and providing a dry lubricating film that survived conditions where the oil film might be insufficient. Applying it to rocker arm contact faces and allowing it to cure before initial startup reduced the wear rate during the critical break-in period and measurably reduced friction losses in sustained operation. The professional racing world eventually provided the most unambiguous validation. When Honda's factory-backed teams in the SCCA World Challenge Series encountered reliability problems in the early 2000s that their engineers could not resolve quickly, team management brought in several independent mechanics from the Southern California performance community as consultants. These were not Miguel specifically, but mechanics who had trained in the same tradition and shared the fundamental philosophy. The problems the factory teams were experiencing included bearing failures at specific RPM ranges during sustained high G cornering, oil starvation under combined braking and lateral load, and valve train instability at sustained high RPM. The independent consultants identified all three problems through methods that the factory engineers found difficult to process initially. The bearing failures were caused by a harmonic resonance in the oil pump drive gear at a specific RPM range, creating cavitation in the oil delivery that starved the bearings in brief but damaging pulses. The diagnosis came from listening to the engine at that RPM range with a mechanic's stethoscope and hearing a faint regularity in the noise that should not have been there. The oil starvation problem was identified by hand measuring oil temperature at various points in the system under simulated cornering loads, using temperature-sensitive paint that changed color at specific threshold. The heat patterns revealed that the oil was pooling away from the pickup in one specific combination of braking and lateral G that occurred at two corners on the circuit. The solution was a modification to the baffle design inside the oil pan, fabricated from sheet aluminum and welded in place by hand. The valve train instability was the most technically interesting problem and the one where old-school knowledge most clearly outpaced modern diagnostic method. Factory engineers had been trying to address it by reducing valve spring pressure, assuming the instability was caused by spring harmonic. The independent consultants suggested the opposite. The springs were already below the threshold needed to maintain valve contact at the highest engine speeds, and the instability was the valve floating rather than the spring resonating. The solution was a spring with 20% higher seat pressure, which the factory had rejected as likely to increase cam lobe wear. The independent mechanics coated the cam lobes with moly, installed the stiffer springs, and the problem disappeared. The legacy of what these mechanics built extends well beyond the specific cars they modified and the races those cars won. It represents a philosophy of engineering that the mainstream automotive industry has been slowly and somewhat reluctantly rediscovering as the limitations of computer-managed mediocrity have become more apparent over time. Look, modern manufacturers have reintroduced many of the specific techniques that Miguel and his contemporaries were applying by hand in small garages. Plasma-transferred wire arc coatings on cylinder bores replicate the surface finish benefits that careful honing achieved manually. Variable valve timing systems accomplish dynamically what Miguel achieved statically with adjustable cam gears carefully degreed to an optimal position. Asymmetric combustion chamber geometries in modern direct injection engines mirror the careful shaping that was done with handheld grinding tools. The difference is scale and consistency. The manufacturers can apply these techniques to millions of engines. The individual craftsman could apply them to dozens. But the underlying understanding is the same, and in some cases, the craftsman's implementation was actually superior. Hand porting still produces better results than CNC porting in controlled comparisons, and the reason comes back to the same principle that made Miguel's approach work in the first place. A CNC program cuts the path it is programmed to cut, and that path is designed based on measured data from sample castings. The program does not know that this particular casting has a slightly thicker wall on the exhaust side that can accommodate additional material removal, or that the short side radius in this specific head casts slightly differently than average and responds better to a different curvature profile. The skilled human eye and hand see what the data does not capture and respond to it. Mechanical fuel injection systems, when properly calibrated, still provide better throttle response than electronic injection in applications where immediate response is more important than fuel economy or emissions compliance. The processing delay inherent in any electronic control system, even one measured in milliseconds, is physically real and its effects are measurable in competitive conditions. A mechanical system that responds to throttle position through direct linkage has zero processing delay. For a driver trying to manage traction at the limit of adhesion, zero delay matters. The data validation point deserves one more visit, because it connects the old and new in a way that is genuinely moving if you think carefully about what it means. When those affordable data loggers became available and people started instrumenting engines that had been tuned the traditional way, they were expecting, at some level, to find gaps. Areas where the empirical approach had missed something that a more systematic analysis would catch. What they found instead was that the empirical approach had not missed much. The timing curves were correct. The fuel distributions were balanced. The volumetric efficiency numbers were what good engineering predicted they should be for the modifications made. Here is the thing. 40 years of doing something, really doing it with your hands and your ears and your feel, is a form of data collection that is every bit as valid as any electronic instrument, and in some ways more integrated because the pattern recognition happens in a human mind rather than a spreadsheet. Miguel did not know that his timing curve matched what engineers would later call MBT timing because he had read about MBT timing. He knew it because when he found that timing, the engine ran better. The academic terminology and his practical knowledge were describing the same physical reality from different directions. The cultural story that runs beneath the technical one is, if anything, more important. These mechanics were immigrants who arrived with skills that the country they came to had decided were obsolete. They were working in garages in industrial neighborhoods, mostly invisible to the mainstream performance industry, maintaining and transmitting knowledge that the mainstream had abandoned. And they were producing results that the mainstream could not explain or replicate. That is not a small thing. The racing victories were satisfying and the time slips were undeniable, but what they represented beyond the sport was the validation of a way of knowing. A demonstration that the knowledge earned through decades of direct experience has a depth and a reliability that cannot be replaced by following a procedure or running a program. When a young engineer with a graduate degree brought his turbocharged Subaru to Miguel's garage and waited in line behind mechanics and racers who had been coming for years, that was an acknowledgement, in the most direct and unambiguous way possible, that something real was available in that place that was not available in any more modern or institutional setting. The apprenticeship network that these mechanics built is still operating today, though the specific engines have changed. The principles have not. Miguel retired in 2018, though he still occasionally consults for former apprentices who encounter a problem they have not seen before. His apprentices now work on turbocharged K-Series Hondas, on late-model Subarus, on BMW inline-sixes. The specific challenge of each engine is different. The approach is the same. Understand the physics. Measure everything. Optimize the foundation before adding anything. Trust your senses and verify with instruments rather than the other way around. The philosophical question that this story raises is worth sitting with for a moment, because it applies well beyond automotive performance. In our general cultural relationship with technology, We have developed a tendency to assume that newer methods replace older ones because they are superior in every meaningful way. We assume that computer-managed systems are more precise than human hands. We assume that algorithmic optimization produces better outcomes than accumulated experience. We assume that the old ways are old because we found better ways, not because the economic incentives of mass production made the old ways impractical at scale. Here is what most people do not realize. These are different things. A technique can be economically impractical for mass production and still be technically superior for a specific application. A computer-managed system can be more consistent across varying conditions and still be less precisely optimized for a specific set of known conditions than a human expert who has spent decades working with exactly those conditions. The choice between old and new methods is not always, or even usually, a choice between wrong and right. It is more often a choice between different trade-offs, and the wisdom is in knowing which trade-offs serve your specific situation. Miguel Santos knew which trade-offs served his situation. He was not building engines for drivers who needed them to start reliably in Minnesota winters or survive owner neglect. He was building engines for people who wanted to go as fast as possible in a quarter mile and who would care for their engines accordingly. Within those constraints, every compromise that mass production required was a compromise he did not have to make. And he did not make any of them. The next time you watch a worn-looking Honda walk away from something that should be several classes faster, consider what might actually be happening under that hood. Consider that the performance you are seeing might not come from a parts list or a tune file or a dyno session. It might come from someone who has spent decades learning to hear what an engine is trying to tell them, and learning to respond with tools that have not changed in 50 years but whose application has been refined through a lifetime of careful, patient, obsessive attention. The bolt-on era eventually ran its natural course, and the performance community has gradually been coming back to fundamentals. Engine builders who understand volumetric efficiency and thermal management are once again valued in ways they were not during the peak years of the plug-and-play electronics boom. The old school is having a quiet renaissance, and the mechanics who never abandoned it are finding that a new generation wants to learn what they know. What is your experience with this side of performance? Have you encountered the old school approach directly, either in your own builds or in cars you have raced against? Have you had the experience of an expert mechanic identifying and solving a problem that computer diagnostics could not find? Drop your story in the comments below, because the community that has developed around this channel is full of people who have been in exactly that situation, and those conversations are some of the best that happen here. If this kind of deep dive into the real engineering behind automotive performance is what you come here for, then you are exactly the person this channel exists for, and there is a great deal more where this came from. The subscribe button is right there, and every video we make is built on the same commitment to going deeper than the surface, past the marketing claims and the forum mythology, into the actual physics and the actual human stories that explain why some cars are fast and others are not, and why some knowledge never actually becomes obsolete no matter how many times the industry decides it has. The greasy hands still know things the clean screens have not figured out yet. And that story is nowhere near finished.